we should be able to do the exact same thing with the right endpoint approximation that we had a moment ago. So again, a Riemann sum is what we were doing. I want to give a formula when you're doing a right endpoint approximation. So moving down here, what really happened? What abstractly could we say we were doing here? Well, here was f of 0.5 was our first height. So that was f of the starting point 0 plus a single delta x already, right? So in some sense, in comparison with the left endpoint, right? If you think about it a little bit, what we did was the first one here was f of a and no delta x movement because we're on the left-hand side of the first subinterval. But here, we've already moved to the full right-hand side of the first subinterval, right? A plus delta x, which is actually the second term over here in this expression. So it's kind of like the left endpoint approximation is backed up in a sense. You're going to lose this term. You don't really start with this one, okay? And then this one will not be sufficient. We'll have to add on one more at the end. Okay, so we're going to lose this one basically and add on a new one at the end. Is the main idea, the main difference between the left and right endpoint approximations. So the first one was a plus delta x, that gives us 0.5 in here, right? And then times delta x. And so forth for all of them. The next one is just another movement of delta x inwards, right? f of a plus 2 delta x's. Gives us the next location of 1, right? Another 0.5 in gets us to 1. Same idea as before. Just a little further in from the beginning. Already at the start, we're 1 delta x further in. So that means we're going to end on 4 delta x instead of 3 delta x like we did for the left endpoint approximation. So the formula should be remarkably similar. We just need to adjust for the fact that we mentioned a moment ago. Okay, so there's our abstract formula for this problem, again specific to the fact we're using 4 rectangles, right? Because they're right endpoints, we already moved in a delta x from the left-hand side of the interval. All right, so if we increase this to n rectangles, an arbitrary number, because it could be problem dependent, it could have 8 rectangles, 4 rectangles, 5 rectangles, who knows how many the problem gives us. Then moving delta x outwards, right, take it out, we'd have the sum of f of a plus some number of delta x. So it looks very similar to the right endpoint approximation formula, right? Right endpoint Riemann sum. But the main difference is we're not going to start at 0. Because starting at 0 means you're starting at the left endpoint of the whole interval. But when you're doing a right endpoint approximation, you're already starting at delta x in. So I need to start with the number 1 for I. Right? And here we had 4 rectangles, 1 delta x, 2 delta x's, 3 delta x's, 4 delta x's, got us 4 rectangles, so therefore I have to end on the actual value of n this time, right? Whatever number of rectangles it is. So again, writing this with the delta x in the usual location, which is to the right-hand side of this expression. Right? A plus I delta x times the base length delta x is what the book calls R sub n. It's the right endpoint approximation Riemann sum using n rectangles. Okay, where delta x, as in the left endpoint case, delta x is always the same. Delta x, as I wrote before, is always the length of interval, as a b minus a is length of the actual interval you're dealing with in the problem, not subintervals, over number of rectangles chosen. Okay? So there's our right endpoint formula. And an important thing to note about these types of problems, from the graphical perspective, since I still have the picture right here, is that as you increase the number of rectangles, it's probably obvious intuitively anyway, if you were to increase the number of rectangles, the approximations should get better and better. If you double the number of rectangles here, right, the approximation will get better and better. So the reason we had such a, you might say, poor approximation in the beginning, right, we determined that the actual area here was between 1.75 and 3.25. That's a pretty big gap for those size numbers. was because we were only using 4 rectangles on the left endpoint and 4 rectangles on the right endpoint. So therefore, we didn't get very accurate values in the first place. If we'd increased the number of rectangles to 8 or 16 or something larger, these values would close in what the actual area was, right? The problem with that is the computations become very difficult very quickly, right? Because the numerous amount of computations you have to make for that number of rectangles. So this is already giving us an idea of why we need to have more efficient means to compute these areas.